This is the second note of the last unit on probability. So the first note we talked about experimental probability. This note we will be discussing theoretical probability. So theoretical probability is another measure of the likelihood of an event. Without performing experiments, theoretical probability measures possible outcomes. Okay, so without performing any experiments. Okay, so the formula for theoretical probability is the probability of an event is, again, the number of successful outcomes divided by the total number of possible outcomes. So not very different really than experimental probability. Okay, so to calculate theoretical probability, all outcomes must be equally likely. What this means is each event has the same chance of occurring because the conditions are fair. So like flipping a coin, it's either going to be heads or tails, and those have an equal likeliness of getting flipped. Okay, so again, the probability of an event is a value between, you should know this, 0 and 1. Okay, again, that fraction decimal percent. So let's recall the coin flipping experiment and use a tree diagram to help determine the possible outcomes. Okay, so on our first flip, so coin 1, our first flip, we're either going to get heads or tails. Okay, our second, if we flip 2 times, again, we're either going to get heads or tails for the first, heads or tails for the second. Okay, when we're flipping 4 coins here, again, each of them has a possible head, a possible tail. Heads, tails, heads, tails, heads, tails. Okay, now the 8 possible outcomes can be grouped into specific events. Okay, so we are flipping just the coin 3 times. These are just the options. So option 1 is we could get heads each time. Okay, so possible outcomes, heads, heads, and heads. Okay, or we could get heads, tails, tails. Okay, we could also get, I'm not going to show you on the graph the whole time. We could also get heads as the first one, heads as the second, and tails as the third. We could get heads as the first, tails as the second, and heads as the third. Or we could start off by getting tails first, right? So maybe our first roll or our first flip, we get tails. And then we get heads for the other 2. Maybe we get tails for the first, heads for the second, and tails for the third. Or we could get all 3 tails. Or we could get tails for the first 2 and then heads. So if you look at these, you'll notice that they are all different. Okay, and they are coming from this table. So I have heads, heads, heads circled in green, heads, tails, heads circled in purple. I could also have gotten heads, tails, heads, or heads, tails, tails. Which I'm out of colors here, but you should be able to see it. Heads, tails, tails. I'm just going to get rid of that red because it's kind of makes it a bit more hard to see. Okay. So we have 4 options if we get heads first, which is shown by these 2 circles. And I guess I should maybe just show you the other ones. Let me change my color. So heads, 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 tails, tails, heads, tails, heads. Or heads, tails, tails. Okay, so those are all circled. So I'll just underline that one because that's the color I did it in. So if you were to draw those circles again on that the bottom half kind of our tree diagram, you would see tails, heads, heads, tails, heads, tails, tails, heads, heads. Oh no, we already did that one. Sorry. Tails, tails, heads, and tails, tails, tails. Okay, so there's 4 outcomes there are 4 outcomes for getting heads first and 4 outcomes for getting tails first. Okay, so moving on here from that tree diagram. So it says event A earning 3 points. Oh, we're going to change points to tails. I should say tails. Okay, so event A, so earning 3 tails, we can see that that is only going to occur, change my color, that's only going to occur here, right? If we look through those, that only occurs once. So number 7 occurs once. Event B, if we earn 1 tail, so let's look and see, we're just earning 1 tail. So we can see, whoa, that is big. Here we earn 1 tail, here we earn 1 tail, here we earn 1 tail, right? All the other ones have either no tails or they have 2 tails. So that is number 3, 4, and 5. So that happens 3 times. Okay, the next situation, event C, earning 0 tails. So again, we're looking, is there a situation where we earn 0 tails? So I can see here we earn 0 tails. I look through, I see a T everywhere else. So I know that that is just number 1, which occurs only once. So listing the outcomes and the events gives you a more clear indication of the chances of having a particular event occur. In this case, you can calculate the theoretical probability for each of the events. So our first event occurred once, right? So in order to figure that out, using our equation, we have the probability of 3 tails equals the amount of times that it happens, so it only occurs once, and that is out of a total of 8. Okay, so again, putting that into a decimal, 1 divided by 8 is 0.125. 0.125 times 100 is 12.5%. So there's a 12.5% chance that we would end up with 3 tails in our outcome. Okay, the second one here, so the probability of 1 tail, okay, we saw that it was 3 times that happened. Again, that's out of a total of 8. Okay, 3 divided by 8 is 0.375. Multiply that by 100. That means that the chances of getting an outcome that has 1 tail is 37.5%. So obviously we're going to have a higher chance of getting 1 tail than we are of getting 3 tails. Okay, and the last one, the probability of 0 tails. So that only occurs if we have all heads, which is 1 out of 8 possibilities. Again, you're going to divide those out, 0.125, multiply by 100, tells us that this will only occur 12.5% of the time. Okay, so notice how we didn't actually flip a coin here, right? We just talked about all of the possible options if we were to flip the coin. Okay, we didn't actually do an experiment where we flipped the coin. Okay, so let's do a couple more examples. So example 1. A standard deck of playing cards has 52 cards, 13 of each suit. If one card is drawn from the deck, find the probability of each event. Okay, so again, we're just using our formula here. So the probability of a heart equals, okay, so however many hearts there are, we know that there's 13 of each suit. So there's 13 hearts out of a total of 52. Putting that into lowest terms, or dividing it out, you would notice that you would get 0.25, which means that is a quarter, which means there's a 25% chance, which makes sense, right? There's 4 suits. You probably could think logically about that and not even do that math. Okay, probability of getting an ace. We know, or we should know, there's 4 aces in a deck of a total of 52. Again, you want to reduce that to lowest terms. If you divide by 4, this is a 1/13th of a chance of pulling an ace. And that as a percent is 7.7%. And again, remember you have to go to a decimal first, which I did, I just didn't write it down. All right, next one. Probability of a heart, a club, or a jack. So first of all, we need to just kind of remember, like think about this logically first, right? So for hearts, there's 13 total hearts, right? Clubs, there's also going to be 13. There are 4 total jacks, but 2 of them are already accounted for. So 1 jack there, 1 jack there. Whoops, that is a 5. Okay, so we've already accounted for the 2 jacks, so there's only 2 other jacks, right? We don't want to account for 4 jacks because we've already included the heart jack and the club jack in that 13. So the probability of a heart, what's the club symbol? No, that's spade. I don't know. Club or jack. Okay, what we have to do is we have to add these together. 13 plus 13 plus 2 over a total of 52 equals 28 over 52. Again, we want to reduce that to lowest terms. So we're going to divide by 4. That gives us a total of 7 over 12. So 7 divided by, or sorry, not 12, 13. 7 divided by 13 times 100. So we have a 53.8% chance of drawing a heart, a club, or a jack. Okay, last one in this example. What is the probability of us drawing a heart, a club, a spade, or a diamond? Okay, so the probability of all of that, the probability of suits, I'll say, we know there's 13 hearts, there's 13 clubs, there's 13 spades, and there's 13 diamonds, and there's 52 cards in total. If I add 13 plus 13 plus 13 plus 13, I get 52 over 52. Divide that out, that equals 1. That means there's a 100% chance that you're going to draw a suit, right? Which makes sense because this is assuming there's no jokers in your deck, okay? All right. One last example here. It says Jason rolls a regular 6-sided die. Find the theoretical probability of each event. Express your answer as a fraction in lowest terms and as a percent. Okay, So we have just a regular six-sided die, which we should know has options of 1 through 6, right? So we need to figure out the probability of rolling a 6. So again, we're just using that equation. So the probability of getting a 6, that's only one side of the die, right? It's not like the die has multiple sides that are 6. It's only one side out of a total of 6. Okay, so to figure out that percent, again, we're going to divide 1 divided by 6 times 100 is 16.7%. And you can skip this step entirely because it doesn't even ask you to put it into a decimal. Okay, the probability of rolling a number greater than 2. So again, we have options 1, 2, 3, 4, 5, and 6, right? So for A here, we had only one chance of getting 6. This time we're asked, what about rolling a number that's greater than 2? So that means we need to see what's the probability of rolling a 3, a 4, a 5, or a 6. So there are 4 options there, right? So the probability of getting a number greater than 2 is now 4 out of a total of 6 options. Okay, reduce that. So divide by 2, that's 2/3. Again, 2 divided by 3 times 100 will give you that percent. There's a 66% chance that we would roll a number greater than 2. Okay, rolling an 8. So as we know, our numbers on a die only go up to 6, right? So the probability of rolling an 8, well, first of all, there's no chance of getting an 8. So 0 successful outcomes out of a total of 6 means there is a 0% chance of rolling an 8, right? It's just not going to happen with one dice, or one die rather. Rolling an even number. Okay, so we have to look and see how many even numbers are there. So there's 2, 4, and 6. So the probability of rolling an even number. So the 3 outcomes that are even, right? There's 3 out of a total of 6. If we divide each of those by 3, that's a half, which we should know is 50%. So there's a 50% chance of us rolling an even number. There would also be a 50% chance of us rolling an odd number, right? Because we have 1, 3, and 5, 3 options. Divided by 6 is a total of 1/2. Okay, so we don't actually have to always do the experiment to be able to make predictions. So this is the end of the second lesson of the probability unit on theoretical probability.